Everybody, welcome. Happy throwback day, y'all. Excited to see who's gonna win today. Seniors, juniors, I don't know. Welcome everyone. Let me go ahead and just make sure I'm adding everyone who's trying to join. All right, so let's do some attendance check. I want to verify to make sure who's absent, who's here. Our question for today, January 26th. I keep trying to update these and I always miss little details, but the question is, what makes you feel energized? And we're going to go ahead and put that into the chat. What makes you feel energized is the question. And it could be anything. And good morning, y'all. It's so cold. Ooh, sweets, to be honest. I know yesterday someone said candy, and I'm like, okay. My sleep makes me feel energized. Yes, I agree. If not that, music, got some coffee, a good night's sleep. Playing Miss Clark and Uno. Yeah, games does make you energized, like those competitive games. We got sleep, we got some food, Starbucks, music, sleep, music. Awesome. Yeah, I'm so happy y'all brought up sleep. That's true. If we don't have good sleep, we're not going to feel energized. And we have food. I don't know. For me, when it comes to food, I feel like I kind of always overstuff myself and I get like the food coma. I get sleepy after I eat, but that's me. Unless I eat lightly. Dancing, working out. Yeah, working out, exercise. And then we have tennis. Yeah, so for me it would definitely be I agree with sleep, um, exercise, and sometimes fresh air. Fresh air, even if it's cold out there, it helps me feel energized. Like if y'all remember when we used to try to go to school in the morning. I know some of you are at school. When you step outside and it's so cold and you have your big old jacket and you just feel woken up from the cold air and just energized. I'm gonna say this though. Coffee for some reason does not wake me up. I just like to drink coffee. I like the taste. It warms me up, but does it really wake me up? Not really. I'm happy no one said energy drinks too. All right, let's go ahead and see who we're missing and who we have. I want to make sure I capture everyone who's here. Make sure I don't miss anybody. All right, correct me if I'm wrong. So let's see. This is who I'm missing, y'all. I'm missing Kalia, Justin, Jayla, Ernesto, Jose, Jonathan, Amara, Porter, and then Sakaya. So that's who I'm missing. Please let me know if I'm incorrect. We just got Ernesto though. Welcome, welcome for those that just came in. Oh no, somebody actually said energy drink. Wait, yeah, I'm like, wait, what a sec. I'm like, where's Alexander Jimenez, y'all? We just got bombed on the wrong person. Anyways, Jose, we got Jose here. Welcome, welcome. Let me just make sure I update the attendance. Yeah, so actually, I'm glad someone brought up. So my first year of teaching, I actually used to drink energy drinks, and that really was so bad for me. I would drink it, I'd feel energized for like an hour, and then afterward I feel a horrible crash. So yeah, energy drinks are pretty, yeah. Try to stay away from those. All right, thank you all for sharing. Let's jump into our agenda today. So today we just took some attendance. We're going to be doing what I call interactive notes. And remember, y'all, what that means is we're not copying down notes anymore on a piece of binder paper. We're actually following along on our own copy of the slides. You all have access to the slides. They're on Google Classroom, and I separate them by day. And how today the credit will go down. So instead of me actually collecting notes and giving you credit for that, it's actually you participating in the Padlet. And that's going to be our credit today. We have Padlet participation, and then there's a checkout with the Google form. So that's our credit for today. We definitely want to rack up our credits because This is the last week in the module, and we have that mini final. We're gonna turn in the final draft of that on Thursday. The mini final first attempt was indeed posted and due. It was due yesterday. Of course, you're still free to get the mini final attempt in, but we're gonna be working together as a class in groups on the mini final in our next class period. So don't be too like stressed about it because we're gonna have time to look at it together. There's gonna be time where I get to give you all as groups feedback as well. But I definitely did wanted you to first give it an attempt before we talk about it, like actually read through it and try it out before we get some feedback. So there's that. Let me know, does anyone have any questions about this? I'll just pause for some questions. All right. If no one has any questions, let's jump back into our interactive notes. Let's rack up some credits, everybody. Okay, just as a reminder, we had these essential questions that we were thinking about, and we kind of got started on these notes the other day. We're going to continue this. And again, you all have your own copy of the slides. You go to Google Classroom and make your copy. So the questions were to think about, how can I determine how fast an object is going at an exact instance? And how is the slope of a function connected to its speed? So this is just some two things to think about as we're doing these notes, because then we'll know the answer to these by the end of today, and I'll be giving you the answer to these in our next class period. Okay, so last time, this is where we left off on our Padlet participation. So let me go ahead and put this back into this chat because we're going to continue on this Padlet. So we're not done yet with this Padlet. And you all can remind yourselves what you wrote. So I asked you a question. Imagine that you have like a ball that's being thrown and it looks like this. You have your y-axis is in meters and your x-axis is in seconds. And I asked you all, what can we do if we want to figure out how fast the ball is going? So let me open up the Padlet with you all. And where we left off was actually in the first column, opener question number 1. I asked you all to either put your name or initials and to tell us like what you thought about what we should do when we try to figure out how fast the ball is going at. And a lot of you gave some great ideas. Most of you were mentioning dividing by time, doing the rate of change, using 2 points to find the average rate of change, and so forth. So these were the comments that we got from last time, and we're gonna build off of that today. So there's just a little for you to review that. We're again gonna continue on this palette because we have 2 more check-in questions to go as we continue our notes today. All right, so this is where we left off last time, everybody. We were reviewing how to calculate the average rate of change. So if you look at the Padlet, you all were telling yourselves that if we want to find out how fast the ball is going, we try to find the average rate of change. And that's exactly what we're doing here. So the average rate of change between any 2 points determines velocity or speed usually. The line that connects these 2 points is called a secant line. And we left off last time actually doing example 1. So I'm just going to kind of quickly refresh you in how we did it. In order to find the average rate of change, you're basically doing the slope formula. And let me show you the next step. When you plug in the y values, after you label your points, so this is going to be x1, y1, then x2, y2. y2. So essentially you see you have 6 minus 9. That's in the numerator, 6 minus 9. And then you have 2 minus 1. That's in your denominator. So it's always change in y over the change in x. And once we complete these, so 6 minus 9 is -3. And then 2 minus 1 is 1. You get -3 divided by 1. -3 divided by 1 is just going to be -3. Now, you don't want to ever forget your units, especially if you have units. So we have meters and seconds. So my rate here is going to be -3 meters per second. That is the speed that the ball is going at between 1 and 2 seconds, because we're doing these 2 points. Between 1 second and 2 seconds. In other words, that's my secant line, by the way, that just popped up. In other words, here's the translation of what we did and what our answer means. So this is saying between 1 and 2 seconds, we are on average going a velocity of -3 meters per second. So velocity is negative. It makes sense because the ball is going downward. As you could see, the slope is going to be negative. It's going down. But if you want speed, all you have to do is make your number positive. So speed, if I was to ask you what's the speed of the ball between 1 and 2 seconds, that would be 3 meters per second. So that's the difference between velocity and speed. Velocity can be negative or positive. Speed is always just the positive of velocity. So let me just pause here to see if anyone has any questions, clarifications on how to find the average rate of change, aka finding the speed or velocity of a moving object. All right. If we don't have any questions on this, let's go ahead and move us on to the next portion, which is going to be, I believe, our check-in. Let's see. Yeah. All right. All right. Here's our first participation of the day, y'all. So, all right, we figured out how to find the average speed between 1 and 2 seconds. But now here's the question. How in the world do I figure out how fast the ball is going at exactly 2 seconds? That is the question that we're going to answer in the Padlet. So you're going to go ahead and go back to the Padlet, and we're going to be answering this in the second column. How do we figure out how fast the car is moving at? Sorry, the ball. There's not a car. The ball. We'll be doing cars in our mini final, but how do we figure out how fast the ball is moving at exactly x equals 2 second? What I'm asking here is for your ideas. Right now, we don't know yet. This is just your question here. How in the world will we figure out how fast the ball is moving at exactly x equals 2 seconds? So exactly at this point, how fast is the ball moving at that instance is my question. And again, we're not copying this down. Everyone's making the copy of the slides and you're following along on your own copy of the slides. Everyone has copy of the slides through Google Classroom. I went ahead and linked up all the slides on there. So we're not physically copying down notes. You're following along with me on your own copy of the slides. All right, go ahead and take your time on that second column. And we're going to take a look at what you all come up with. Again, don't forget to put your name or initial. All right, I'm going to give it some more time there so that we all can go ahead and put up our ideas there on the second column. How do we figure out how fast the ball is going? At exactly 2 seconds. Let me go ahead and just circle this. So y'all know where this is where we're at, and this is where you're putting your name or initials to get your credit here. We're on the Padlet. Oh, okay. For some reason, we can't respond on the Padlet. Let me see if I could. No, it won't happen when I'm trying to paste that response, but all right. So if you had some issues adding your comment, I went ahead and I'm going to put it in for you. There you go. Again, name or initials, totally fine. All right, I'm going to go ahead and start to take a look at the ideas that y'all are coming up with. And then we're going to move on from this. Again, you want to make sure that you put your ideas down here for your credit. Super important. All right, so here's some ideas. It says, how about, sorry for the background noise, how about when the lines connect at one point, like if x was 6? So that's interesting, kind of like, what if we just focus on that point, I think is what the student is saying. I think we would have to, oh, the student's still writing. We need to get as close to x equals 2 and then plug in the x and y's. Ooh, okay. So kind of like moving the points closer. And then distance divided by speed equals time. I don't know, to be honest, that's okay. But we're definitely still going to be working with this formula, the velocity formula. We find the average speed per second using a decent line and the equation. Use the coordinates as close to 2. Make sure that you put your name or initials, because this is really good what we're saying here. By adding or multiplying the x-axis, get close to 2 and plug in the x. So I love this. You see how these are coming up? Like, why do we have to get close to 2? And this one, I would say that we need to find the average and or determine where they connect if they do. And we have a few more ideas coming up. Choose points that are infinitely close to the point of interest and then finding the slope between the 2 points. Wow, we have some pretty good ideas. I'm hearing a lot of get close to 2. Also, we're going to be finding average rates of change. So what y'all are saying is totally on point. That's exactly what we're going to be doing when we're going to figure out how fast the ball is going at exactly x equals 2 seconds. So again, don't forget to finish up your thoughts, put your name or initials for your credit. I'm going to go ahead and move us back onto the slides. Let me just clear my screen. All right. And then we do have one more check-in questions, but let's follow along on the slide. So things we need to know though before we get started on talking about what instantaneous rate of change is. So first off, what in the world is instantaneous rate of change? So the best example that I could think of is this. When you're driving a car, the speed, so think about this, and maybe some of you can answer in the chat. When you're driving a car and you know you're looking at your speed, and this is called a speedometer. When you're looking at your speed, is that an instant speed or is that an average speed? Is your car telling you on average how fast you're going, or is it telling you at that instant moment how fast you're going? So think about it, and or if you think you got it, try to put your answer in the chat. All right, so we have instant speed, average, in that moment. So that's direct messages that we're having here. Let me know if anyone wants to argue that. So I have two that are saying it's an instant speed, one that's saying it's an average speed. All right, y'all ready? So when you're looking at the speedometer and you're driving a car, what you're looking at is actually your instant speed. That is how fast you're going at that moment. So this little red thing right here, it moves up and down and it's constantly changing because it's telling you your instant speed. Your car is not taking 2 points like, oh, between this first minute and second minute, and then calculating the average rate of change. It's not doing that. Your car is actually giving you your instant speed at that moment. Like, you know exactly how fast you're going in the moment. It's not an average, right? It's an actual instantaneous rate of change. So this is like a very clear example of instantaneous rate of change in the real world. And we're going to try to figure out how to figure that out using graphs though. So your car is able to quickly give you that information. Some more things you should know about what is the instantaneous rate of change. First thing, instant rate of change is when you determine the rate of change at an exact instance or an exact moment in time. We and you can estimate the instant rate of change by moving 1 point closer to your point of interest. So a lot of you were saying move the 2 points closer together, move it closer to the point of interest. That's exactly what we're going to be doing to estimate in this class. We're going to be estimating instant rate of change, and we're going to be really close with our estimates, to be honest. And choosing points closer and closer, does that remind you of a big idea? That's something for you to think about. I'll give you a second and I'll let you know what big idea this connects to, or maybe some of you already see that since you're following along with me on the slides. All right, so when we're moving points closer and closer, infinitely closer and closer, what that is the concept of a limit, y'all. So the process of moving 2 points closer and closer together, we're basically applying our big idea of limits. Oops, I don't know if someone has a question. But moving our points closer and closer, that is applying the big ideas of limits. So this is how this unit is kind of interconnected here. And that's why we're moving into instantaneous rate of change. Again, remember, we're not copying down these notes. You're following along on your own copy of the slide. All right, y'all, let's go ahead and apply the ideas that you all came up with and the ones that we just talked about. So we are going to move the point closer. So if I want to figure out how fast I'm going at x equals 2 seconds, what I'm going to do is I'm going to move that green point closer. Notice how I moved it closer from before. It's really close to 2 because my x value is 1.9. So it's close to 2. And this is what we got. So I just used Desmos and I clicked it and I moved the point closer. And here I typed out the strategy. We're trying to figure out how fast the ball is going at exactly 2 seconds. So I'm moving that second point closer to the blue point there. So now let's go ahead and repeat the process. We're going to calculate the average rate of change. But this is going to be a better estimate now. We're going to get closer to what the actual speed is at x equals 2. So I'm going to, again, use my slope formula. Let's label our points. So x1, y1, and we have x2 and y2. Plug those in and we should get 6 minus 6.75. And then on the bottom in the denominator, you have 2 minus 1.9. Use a calculator or use your phone. And you get negative 0.75 divided by 0.1. Divide that. And if you do this division on your phone or on a calculator, you should get that our slope or our average rate of change between these 2 points is negative 7.5 meters per second. Now, again, remember this is a velocity, so it's going negative 7.5 meters per second. If you want speed, you would just say it's going 7.5 meters per second. Without the negative would be speed. So this is what we got when we move the point closer. But we could do even better than this. We can move the point even closer to 2. So that's what we're going to do in the next slide. So I'll pause to see if anyone has questions though on this part, what we did and what our strategy is. Pay attention to the strategy here and how we're applying, those ideas that you all mentioned. All right, let's go ahead and let's do even better. So I'm going to move the point even closer to 2. And again, this is me on Desmos. I'm not actually like plugging into a function or anything. I just graphed the function. I went on Desmos and I'm just clicking the points on there. In the real world, when you apply your mathematics, you'll have these tools available to you. You just need to know how to use the tools. That's why we're so into using the Desmos, because it's a tool that we want to use to our benefit. All right, now in example 3, we're moving that green point, the second point, now even closer to 2,6. As you can see visually, it looks even closer to the point that I'm interested in, my point of interest. So I chose 1.98, comma 6.158. Again, this is just me moving my point closer on Desmos, and we're gonna again calculate what the average rate of change is now. Again, feel free to label your points if it helps you. So this is gonna be x1, y1, and we have x2, y2. And we're going to go ahead and plug in the values that we have, and we're going to see what is the better estimate. So at x equals 2 seconds, how fast are we going? We do some of this math, use a calculator. I get that my slope of the secant line, or my average rate of change here, is going to be negative 7.9 meters per second. So that's my velocity. Again, if I want speed, I just say 7.9 meters per second, because speed is always positive. So I'm getting a better and better estimate as to how fast I'm going, or how fast the ball is going at 2 seconds. So let me pause here again to see if there's any questions or clarifications about what we're doing, our strategy, and or the work that we're doing. All right, y'all. We're going to get ready and now synthesize what we just did. And we're going to be going back onto the Padlet, everybody. And again, if you can't write on the Padlet, you could send it to me and I'll type it out for you. That way I could just record, our credit. So this is what I need you to do on the Padlet in a second. What happened to the secant line when the 2 points were moving closer to each other, right? What was happening to that secant line? And how is what we're doing right now related to limits? Those are the 2 things I want you to think about and try to answer. It's not about being right or wrong. It's mostly for your ideas. So we're going to be on column 3 on the Padlet. So column 3, we're here on the 3rd column. So I'm going to, again, just make sure we all have access to the Padlet. Let me put that into the chat again. And we're on the 3rd column. And what you're doing is answering this question. So what was happening? The secant line is this red line, y'all. What is happening to the secant line when the 2 points are moving closer and closer together? And how is what we're doing related to limits? And you could click on the picture, it's there for you on the 3rd column. So you can see what's happening to the secant line. Okay, thank you for those who are messaging me about why you can't type, but I got you. Again, do message me, but how you write on the Padlet, just so that y'all know, is that there's a little plus sign right here at the very bottoms. And if you click it, it pops up and you can write like your name at the top and then you write your response at the bottom. That's how to work the Padlet. I mean, just delete this. That's just in case if you try that and it doesn't work. It's this little plus symbol at the bottom. But again, send it to me if it's still not working. Someone says, I don't know what to say in column 3. So it's if you're stuck on it, what do you notice and wonder? Uh-oh. I don't know if my little photo here. Oh, it's up here. There we go. So for that person that just anonymously messaged me, said, I don't know what to put. Well, then what do you notice and wonder it's happening here? When we were moving these 2 points closer and closer, what was that red line doing? How are the slopes changing over time? You could put a notice and wonder, and that's okay. But if you definitely want to try to tackle these questions, please go ahead and give us some ideas. Just put a reminder that we're on the third column. Give me a sec. I'm going to try to reach out to students who aren't here currently. All right, I'm seeing some great stuff there on the palette. Again, make sure that you, because I see two anonymous, do make sure you put your name. You could even put it as a comment here too, or you could edit your post as well. So you could add either your initials or your name. All right, let me go ahead and start reading what we have here as far as ideas. So we have here, the secant line is getting steeper. So yeah, 100% I agree with that. I see that mentioned a lot actually. So here I see steeper again, it gets steeper, steeper. So I see that mentioned like the most. The line is getting steeper. So that's how the slope is behaving. The slope itself is getting steeper. So as you can see, that's true. It's getting like the slope is getting more and more negative, which means your line is getting more and more steeper. So I agree with that observation. Next, we have, let me see what we have when it comes to limits. So this one says, I think it's related to limits because we're getting an estimate of where the function is approaching as we input different values. Yes, I love that. So I see that. Um, I see that because right here we got the slope is -3, but then we're going to get even a better estimate when we move our point closer. So then we have -7.5. But then even closer, we get -7.9. You could even keep going, get closer, closer, closer to 2. You will see that the limit is going to approach actually -8. So the actual velocity of the ball at x equals 2 seconds is going to be -8. And you would see that if you tested even closer points. And that's how we're using limits here. Like I would keep going and keep testing it, and you'll see that it's going to approach -8 or 8 meters per second as the speed. So I agree with that. And again, limits to get closer to our value. And a lot of you are noticing that the points got closer. The line gets steeper as the points get closer. I wonder how limits relate to each other. So the limits is basically when you're moving the 2 points closer and closer. That's how limits are related to what we're doing here. In addition, what you're doing to find out the instant speed is you're taking the limit of the slopes, like finding out what are the slopes approaching as my points get closer and closer. And the slope is going to tell me the instant speed or the instant velocity of the ball. Yep, and again, the mention of steepness. Yeah, y'all are perfectly accurate on that. Make sure that we write down our little our name or initials. I see this last person. I definitely want to give you credit. Make sure you add your name or initial. Awesome. We're going to go ahead and move on from the Padlet. Thank you for your contributions. And the last participation point that we'll be having at the end of class is a Google form. That's once we kind of finish up our notes. And that's what we're going to move on to, y'all. All right, we're back on the slides, everybody. So again, you're on your own copy of the slides. You're annotating them, or you're following along with me on my slides. All right, so the question always comes up though. Why can't we just put the 2 points right on top of each other and then we get the instant speed and then find the slope that way? So why not? Let's try this out. And I think somebody said that earlier, like we could put it right, like choose 1 point. Why not? So let's say that my 1 point is at 2,6. Let's say if I only have 1 point, that means this is both my x1, y1 and also my x2, y2. So why don't we just do this then? Like, wouldn't this be the ultimate close point? The point itself. Sorry, this should be y1. So that means if we only have 1 point, that 1 point has to be both x1, y1 and x2, y2. So let's try this out. Why doesn't that work? Okay, using our slope formula, we plug it in. We get 6 minus 6 on the numerator and 2 minus 2 in the denominator. All right, basically that's 0 divided by 0. Now you all can go ahead and on your phone or on a calculator, try to enter this in and see what you get. Pause and try to do this, because then, not everyone believes me if I'm like, well, you can't do that. So try it out. Different things are like your phone, calculator, something else it's gonna give you a different answer each time. But either way, you won't get the same. You're gonna get a problem. So let me try this out. I'm gonna do it on my phone. 0 divided by 0. This is what I get. It says error, and you all can try it out. So 0 divided by 0 gave me an error. And there's a reason for that. So you could try this all you want, but you actually cannot divide by 0. Mathematically, it is impossible. If you're really curious about studying this, there's even videos on YouTube that really explain it well as to why you can't divide by 0. But for the moment, we can't divide by 0. And that's the reason why we can't just put the points on top of each other and try to find the slopes. That's why we got to choose points that are extremely close to our point of interest. And that's how we'll get a very, very good estimate of the instant rate of change. So that's the why of this part. Let me see if anyone has questions. I'll pause here. Okay, great. And then Angelica says it comes out like error. Yeah, same for me. I think when I had calculators in the classroom, it would say like can't div 0 or something like that. It's trying to say error can't divide by 0. At least it gives you a reason. Your phone doesn't really, just says error. All right. We don't have questions on this. Let's go ahead and jump into the formal definition of a limit. And this is what our kind of our exit ticket is going to be based on. Now, this is basically if y'all did your annotations on the big ideas packet, you probably encountered this and you were very confused. So this is the part where I'm going to try to explain it. And you might use this when it comes up in your mini final. And this is going to take a bit of focus. So try to focus your brain and be prepared to have questions not fully understand. That's going to be expected here. But here we go. Step one, I'm going to kind of rename my points. I'm going to call this here point x comma f of x. X is my input, my output is f of x. So that makes sense. The part that might trip you up is how I'm going to name the second point. Now, if this is x comma f of x, my second point has to horizontally move over h amount of units. So you're going to see a little arrow down here, and I'm going to move some units. I'm going to call that h units. If I'm moving over horizontally by h units, what that means is this new point is going to be called x plus h, because I moved over by h. So x plus h is my new input, comma, f of x plus h, because I'm inputting x plus h into my function. So this is like my new renaming of points. And again, I'm going to ask for your full focus. I know this is where it gets a little bit abstract, and that's okay. And we got this, okay. All right, so then if we have this, that means if I'm trying to find the average rate of change between these 2 points, I'm gonna just do the same thing where I do x1, y1. I'm gonna label these and try to set this up to kind of create myself a formula. This is gonna lead us into the formal formula for the instant rate of change. And I'll give a little bit more information about that. So if I label my points, let's go ahead and set up the slope formula. So if we do y2 minus y1, that's where f of x plus h minus f of x came from. Then at the bottom here, x plus h, that's x2 minus x1. So x plus h minus x. So that's where this average rate of change formula is coming from. Now, in my setup, in the denominator position down here, there is something I could cancel out. In the chat, does anyone know what I could cancel out down here in the denominator position? Let's see if anyone knows. Is there a way I could simplify this bottom part? Anything I could try to cancel out or get rid of? Yes, I got an answer here. Direct message, x. That's right. X minus x, that's just 0. So let me cancel that out like so. And then my formal new average rate of change formula becomes this. And you can't really cancel out the stuff in parentheses. They're kind of trapped there. So this is as much as we can simplify. So this is the new average rate of change formula. But in your mini final, you're only expected to do estimates. We're not 100% going to be utilizing this formula, but we do need you to know where it come from and the different components of it, like, oh, this is coming from us renaming our points and then putting it into the slope formula. That's all you need to know basically for this. But you don't have to use it. You just have to understand what its components are for, especially if you're going to be taking calculus next year. All right, we have one more slide, everyone, and then we're going to be jumping into the exit ticket. One more slide. We got this. Let's go. All right, y'all, so you ready? So previously, in this previous slide, we had that this portion right here was the definition of the average rate of change, right? So that portion right there was the definition of the average rate of change. But now we added the limit in front of this. When you add the limit in front of this, it now becomes the instant rate of change definition. The reason for that is because the limit is going to be as h approaches 0. That means that horizontal distance between the points is getting smaller and smaller. So this limit represents the 2 points moving closer and closer together in our slope formula. And this is basically your slope formula. This is your point of interest, y value, your second value, and h was the horizontal distance. In calculus, this definition is known as the derivative. So in your exit ticket, you're just going to be asked to identify the different components of this formula. Again, you could reference this formula and use it in your mini final if you are striving for advanced. So that is an option, right? And you could work with me in office hours too if you'd like to have some more support on how to use this formula. But for now, you're just going to be asked to kind of identify why each portion of this formula makes sense when we're trying to define the instant rate of change. Um, Let me know if anyone has questions. I'll pause here and then we're going to get into our exit ticket. All right. For those of you who have my slides, you do have access to the exit ticket, but let me go ahead and give everybody the exit ticket. So here we go. I'm going to go ahead and copy this and put this into the chat. Here is the exit ticket. That is the last thing that you're going to be asked to do for your credit today. Remember, I'm not collecting notes now. You just basically want to open up your own copy of the notes and you follow along and annotate your notes as as you make sense of all this. So when you open up your exit ticket today, you're going to be asked for your email address. Number one is going to ask you in your own words, how do we approximate the instant rate of change? And let me just remind you all, we were approximating the instant rate of change here. When y'all were answering this in the third column, that's exactly what we're trying to do. When we're moving the 2 points closer and closer, it's us trying to approximate the instant rate of change. So it's kind of asking you in your own words, how do we do that? Number two is going to ask you to explain also in your own words, why in the world do we need this here limit right in front of the instantaneous rate of change definition? So asking you why we need this. Now you are totally free to go back to our slides, slide number 15, and I totally pointed an arrow as to why we need that limit. So use your slides as your reference. You could even use slide 14 to kind of explain where all of it's coming from, but it's just asking about why do we need that limit in front of it for the number two. All right, does anyone have any questions about our exit ticket, about how to get this in or anything like that before we get started on it? All right, if no one has any questions about this, let's go ahead and get our credit, y'all. So again, it was Padlet plus exit ticket. You're gonna be seeing this entered in right after our class today because we have lunchtime coming up. So I'm gonna go ahead and mute myself, get this in. We're gonna be on for 5 minutes and I'll check in at the last 5 minutes and once the time runs out. All right, everyone, good luck on this here exit ticket. And it's just an exit ticket. Don't feel stressed about it. All right, everybody. So it's lunchtime right now. Do make sure that you submit the Google form. I'll be checking it later today. You all enjoy. Bye, everybody. I'm gonna go ahead and end this.